Okay, so okay. So we are happy to have Shamik telling us about the particles at null-infinity. Yeah. So first of all, I'd like to thank the organizers for giving me this opportunity to talk here. So this is actually a strange title, and most of the things are actually very, extremely simple that you will see. And the thing is that this talk is actually primarily based on this set of works, and then I have also done something. So it's actually based on all these 5 works. Okay, yeah. So let me just give you something. So actually, we know that in Minkowski space, the natural boundary at infinity, it's a null boundary. So let me just draw the Penrose diagram of the Minkowski space. So this is the, say, the Scri plus, this is Scri minus, and then you have these spheres here. Okay, and you also have this geometry. And so if you have a massless particle in Minkowski space, then what it does is that you can think that as time t goes to minus in infinity, it actually starts at some point here, and then it goes directly to the Scri plus. Okay, so now the thing is that, so recent understanding of the relation between the soft theorem and asymptotic symmetries in flat space suggests that perhaps there is some kind of a quantum field theory which lives on null infinity, which actually computes the S matrix of the flat space theory which we have here. And the thing is that it seems that if this sort of theory actually exists, then it should be reached in symmetry. So now, so the goal is actually that to see that if there is any sense in which massless particle, so we will just be working in four dimension. In 4 dimension can be thought of as living on null infinity, which is this Scri plus and Scri minus. And the thing is that, can one construct some sort of, some sort of quantum field theory on this null infinity, which is Poincare invariant and unitary. So the thing is that actually, this is a very complicated thing. But so what we'll do is that, we'll just look at the free theory, in the sense that, we'll just look at the free massless particles. And what we'll do is that we'll construct representation in which you can think of these massless particles as living in this Scri plus minus. And actually, in order to do that, so I have to introduce a bit of notation and convention here. So what I call here is this asymptotic Poincare group. So let me just explain this thing. So what we do is that we have this Minkowski space in 4 dimension, and then we actually write this part of the metric in spherical polar coordinate. So that gives me this minus dt square plus dr square plus this thing, and this d omega 2 square. So this is actually the metric on the sphere. So you can think of this as just the sphere which is here. So every point, roughly, yeah, the metric on this sphere, cross section of this cone. Okay. So now the next thing that that we will do is that we will do this retarded coordinate u as u equals t minus r. And the thing is that once we introduce this, so and also we will introduce this complex coordinate z on the sphere, which is defined in this way. And with this, the metric just becomes this. And this 4 dz bar by this quantity by 1 plus dz bar square. So that is essentially this metric on the S2 written in terms of the z. Okay. So now the future null infinity, which is this chi plus, so you can reach there by taking the r going to infinity at fixed u z bar. So let me just draw this thing. So a fixed u surface is like this. So this is actually you can think of it as a u equal constant surface. Okay, and the coordinate on this sphere is actually the z bar. So this is an S2, which you have here. Okay, and then the thing is that this r is coordinate in this direction. So you are so u z bar fixed means you are fixing one particular point on the chi plus, and then you go in this direction. Okay. So if you do this, so then what we get is that this u z bar. So they are actually coordinates at null infinity, which you can actually clearly see from here. So the null infinity, it's a 3-dimensional structure. So you have these cross sections which are S2, and the coordinates on the S2 are this ZZ bar, and then the coordinates in this direction is just U, okay? So you have this U Z bar. Okay, so now to see that, so now we have got this U Z bar, and now actually we want to see that how this the Poincare group actually acts on this U Z bar. So the thing is that, so for our purpose, it is actually more convenient to think of this SL2C as the Lorentz group, and there is actually a 2-to-1 map from the SL2C to the SO3, and this is actually this stuff is quite well known. So we have a space-time vector x, so which is just the coordinates of a space-time point, and we can associate a matrix, a Hermitian matrix with that, and then the SL2C matrix actually acts on this space-time coordinate x, or this matrix x, in this way that x goes to x prime, where you have this mxm dagger, and this m is actually an SL2C matrix. And from this, you can recover the x prime mu in terms of the x mu. But now, actually, this lambda mu nu, which are the Lorentz transformation matrix, they actually become a function of this m. Okay. So now, so under the SL2C transformation M, the Bondi coordinates in the bulk, which are like this R, U, Z, Z bar. So they actually get transformed to something like, say, let's call that M, R, U, Z, Z bar. And that actually one can easily find out from here. But it turns out that if you now take the limit where R goes to infinity at the fixed U Z Z bar, then this transformation actually simplifies drastically, and what you get is essentially this simple looking transformation. At least this part is actually quite well known, that M acting on this U, Z, Z bar. So now this U, Z, Z bar, they are actually coordinates of a particular point on scribe plus. And so the M acting on U, Z, Z bar gives you this, where M is this A, B, C, D, that is an SL2C matrix. And this is, so the SL2C acts on the sphere. So just like the global conformal group, and that's this thing is AZ plus B by CZ plus D, and Z bar also goes to this. And then you have this transformation law for U also. So that transformation law is there, which is extra, which actually tells you that how the Bondi time on scribe plus actually transforms under the SL2C. Now the point is that now if you make a space-time translation by a 4-vector L mu, then actually you can do the same thing, and then actually also it turns out that it's a simple answer if you go to R going to infinity. So that actually gives you this TL acting on UZZ bar. So ZZ bar does not transform under the space-time translation. Only this U transforms. So, and the point is that, so given a 4-vector L mu, so this F ZZ bar L has this fixed form. So you can change L0, L1, L2, L3, but the Z dependence is fixed. And for example, one of the important transformation is just the transformation of the time. So just the transformation of the time is the T. So you have this L1, L2, L3. So if you set L1 equals L2 equals L3 equals 0, then what we will get is that FZZ bar L is just a constant, because you have L0 and L0 from here, and that gives you FZZ bar L. So you just, so the time translation in the bulk just adds that same constant term to U. So U actually behaves like the time. So yeah, so these are the two essential things. So now, we can see that this U Z Z bar at infinity, they are actually closed under the action of the Poincare group. And the thing is that the action of the Poincare group at null-infinity in the coordinates U, Z, Z bar will be called the asymptotic Poincare group, but it's the same as the Poincare group, but it's just acting on a different space. So it is, so instead of the 4-dimensional bulk, it actually acts on a 3-dimensional boundary. And the thing is that so you have the sphere at infinity, which is parameterized by this ZZ bar, and this is also known as a celestial sphere. And we can see that the SL2C, so this is just acting like the group of global conformal transformation on the sphere at infinity. Yeah. Sorry, are you what?
When we have Poincare invariance, we like have the translation invariance with respect to all the coordinates, right? Means
yeah. So you have, so you mean this thing that some x mu going to x mu plus a mu?
Yeah, means here is only U is shifted.
Yeah,
but
here only U.
Like Z and Z bar, that is including the SL2C. That's what you're saying.
Yeah. So this Z and Z bar will not shift. I mean, that's what you get actually. I mean, if you do this thing, and only this U will shift in this, and it has this particular form. Yeah, yeah. I mean, once you take the arguing to infinity limit, those things drop out.
Of this asymptotic group at null infinity?
Well, so this is a convenient description, and what I will show that this is essentially the coordinate which you get from the quantum field theory also. So you don't really need to go into the bulk and get this transformation. So these are actually the natural quantities which also appear in the quantum field theory context. So I mean that I'll come on to that actually. But yeah, so in the bulk actually you can do it in lots of other ways, but this is a particularly convenient choice. And this is also quite natural if you look at this particular diagram, that you have a sphere cross section here, which is S2. And then these ZZ bar actually are coordinates on this S2. Yeah. Okay, so now let me state the results. Okay, so results for what? Okay, let me go back to this. So basically, some kind of, well, so let's, we'll construct some kind of free theory, which will have this kind of transformation, which will transform nicely under these things. Okay, so but let me just, yeah. So now let's look at the quantum field theory situation. So now we have these massless particles in 3 plus 1-dimensional Minkowski space, and it's and we know that the single particle quantum states of these particles can be written as p mu sigma, where the p squared p is null and sigma is spin. Okay. Now the Poincare transformation. So this is a particular Poincare transformation. So this is a space-time translation with 4-vector mu, and this lambda is the Lorentz transformation, and this actually acts on x mu like this. And we know that if this u lambda, so u lambda is the unitary representation which actually acts on the state p sigma. So if you act on this state with this, you get this phase factor, and then of course this is the space-time translation. So you get this simple phase factor, and our states are actually normalized like this. So now the point is that the same thing actually, if you just go back to here, so the same thing which we did for the vectors in the Minkowski space, so we can actually do the same thing for the null vectors in the P space. So you have the SL2C acting on the vector P mu. So one good way to define that is that I mean you define this Hermitian matrix, and then this SL2C a matrix M acts on this like this. So you get again a transformation like this. So now this lambda mu nu depends on M. M is some SL2C matrix. And then the point is that, so now let me draw this picture in P space. So I have this P space and I have this cone. Okay, so P0 is always greater than 0. Okay, greater than equal. Okay, yeah, I mean, there is a tip of the cone. But the thing is that, yeah, so you have these null directions. So, okay, so this is actually an S2. So this is a cross section of the cone. So the cone is 3-dimensional, and this cross section is 2-dimensional S2, and you have these vectors pointing like this. So they all lie on this cone. And if you don't look at the magnitude of the vector, so if I write p mu as some p0 and p, and then basically the space of null directions is actually given by these ratios. Okay, so this is the ratios which actually give you a particular null direction. And the point is that you can just see from this picture that this essentially gives you the S2. Okay. And P is of course null, and that's why you get an S2. Okay. And so on this S2, we can introduce this complex coordinate Z, and then the point is that you can just check, it's an easy thing, that if you do this SL2C transformation on P, then what you get is that Z goes to Z prime, which is this form, this AZ plus B by C plus D. So SL2C act on this S2, the space of null directions, as a global conformal group. Okay, so now this is same type of parameterization, like the going to the spherical polar coordinate. So you can write your null vector in this form, then this theta phi, so that becomes the coordinates on the two sphere, and if you substitute it back into this relation for Z, what you get is that Z is tan theta by 2 e to the power I phi. So let me just mention one thing, which is that in the literature, what is usually in this soft theorem literature, what they do is that they basically do the stereographic projection from the south pole. But well, sometimes, I mean, probably more, it is more conventional to do it from the north pole. So that's why you get this tan. Otherwise, you will get this cot, I mean, which you will see in most places probably. Okay. Okay. So now, with these things, now let us define the state. So this state, you can define the state. So let me explain what this thing is that. So I am defining the state H bar, Z bar, as so Z bar is this state, the same thing, this Z. Okay. So this is the coordinate on the S2. So now, so I have this particular normalization factor. This lambda is a real number, and this UR ZZ bar, so that's a rotation operator, which I have chosen to be which I have chosen to be of this particular form. And the thing is that the H and H bar have this particular, so this, then you have this UR ZZ bar, and then you have this integral over the E, and then you have this particular state. So this is the state where the massless particle with helicity sigma moves in the Z direction. And the thing is that the H and H bar have this particular form. Now, these states are actually, they form an orthonormal basis. So if you compute this thing using this, then what you basically get is this delta sigma prime, and then delta lambda minus lambda prime, delta to Z minus Z prime. And they also form a complete set. So you can write the identity as an integral over these states, which is the standard thing. Now the interesting point, it's way overcomplete.
Coherent state representation.
This is coherent state representation.
Final line.
Why? I mean, they are just, these states are like
No,
this.
the final line, equation 24. I was wondering whether they are just complete or over complete.
No, why it's a coherent state representation? Oh, no. I think you are making a mistake. I mean, it is not a coherent state representation. I mean, well, I mean, it is just, it is just some way of, I think, you could just write it as dx dy. It is actually that. So x, y are just two real numbers, okay, and then you have this d lambda, which is 1. Is that fine? No, this z, yeah. So this z, at least now actually, and as Rajesh actually mentioned, so coherent states they do not form. Yeah, you have this thing actually, okay, which tells you that it is not a coherent state. Yeah, so these states are orthogonal. Now, the point is that, so given this definition of this state, what you can do is that you can see that how an SL2C transformation actually acts on this state, and this actually acts in a very nice way. So U lambda acting on this state, this H bar, Z bar, gives you this state, and you have this particular, this little group factors, which have this form, this 1 over Cz plus D to the power 2H and 1 over C bar Z bar plus D bar to the power 2H bar. And let me just remind you that H and H bar have this particular form. Now, this is actually very, so this is exactly the same way that the quasi-prime or the primaries of the SL2C will actually transform under a global conformal transformation. And the thing is that, I mean, once you recognize that this factor, this Cz plus D to the power 2H is essentially your D lambda Z, dz to the power H. Okay, so then you can actually get, so this is actually transforming like a tensor of weight H bar, okay? So in these states, so these states actually transform like the primary of the SL2C, which acts on the celestial sphere as a group of global conformal transformation, and the scaling dimensions are now given by this HH bar. So HH bar has this particular form. Now, it is actually just using this, one can check that this is actually a unitary representation of the SL2C, and this is actually known for a long time. So this is called the unitary principal continuous series representation of the SL2C. So now, what is happening here? So actually, let me just give you a brief here to this. The thing is that the difference with the standard Wigner representation is that in this case, so in this case means when you have these states at the basis vectors in the P space. So in this case, one considers the little group of a null momentum direction, which is actually given by this thing. But instead of the little group of a null momentum vector, and that is actually clear from here because this E has been integrated out. Okay? So now, the thing is that these states, I mean, if you look at the standard P sigma states, so they actually form an irreducible representation of the inhomogeneous SO3,1. But the thing is that under the action of the SO3,1 or SL2C, this big irreducible representation of the inhomogeneous SO3,1 actually decomposes into an infinite number of irreducible representations of the SL2C indexed by HH bar. Right, so that's what is happening here. So you can just think of this part as the for a fixed lambda and sigma. Well, so sigma here I have just fixed it, so that's why there is no sum over sigma here. So for a fixed lambda, you can just think of this as a representation of the SL2C, and then the point is that this P sigma, the standard representation, they are built out of this representation by varying this lambda. So this is the quantity which you have. Okay. And here actually just from the transformation you can see that a fixed lambda sigma, these states indexed by ZZ bar, they actually form an irreducible, well, I haven't shown that irreducible, but it is known that it is an irreducible representation. So a massless particle described by this state, this HH bar, ZZ bar, this can be thought of as living on the S2, the S2, I mean this is S2 actually. On the S2 in the P space with coordinates ZZ bar, and we can think of this HH bar as this internal quantum numbers of these particles. Okay. So now, yeah.
The ZZ bar of the momentum with the ZZ.
No. Yeah. So these ZZ bar has nothing to do with this. So once I take into account that how the space-time translations actually work, then actually you can say that, well, these ZZ bar you can identify with this. But so far, ZZ bar is just P space. I mean, yeah, I should have called it some W bar actually, probably, but I have used the same. Okay, so now the natural question is that how does the space-time translation actually works on these states? So let me just tell you that these states you can, somewhat imprecisely probably, but you can think of these states as living on the S2. Okay, so and these are like some kinds of position eigenket. In fact, probably it's not a very bad thing, because you could probably define a z hat as some p1 hat plus I p2 hat. And well, I mean, this will have some singularities, but it's an, I mean, there's no operator ordering ambiguity here. So you could perhaps define this z hat and say that, well, these z bar actually are eigenstates of that. So they are actually some kind of position eigenstate of a particle which lives on this S2. And now, so by analogy with the non-relativistic quantum mechanics, let's define these states, which I call this HH bar U ZZ bar, as just e to the power IHU acting on this state. So these states are just like they're defined as TX. I mean, usually we define these states in E as like these TX states, which are like e to the power IHT x. Okay. Now the point is that it turns out that now, if you act on this state, now, so you have this thing, so you have a massless particle which is actually described by this state, this HH bar, ZZ bar, so it sits, say, at a particular point of S2, and then you actually translate that in time for some amount u, and then you get this state, and now you can act on that state with this SL2C or the Lorentz transformation, and that state now actually transforms like this. So u lambda acting on this is a that this HH bar, u has this form, and ZZ bar, of course, it's the same form as this. So the extra thing only is u, and the point is that u transforms in this way. And then you can also easily show that this, if I now make a space-time translation to this, this u should be actually here, okay? And now if I make a space-time translation on this state, what I get is just HH bar u plus f ZZ bar L ZZ bar, and f ZZ bar L has this particular form, where L mu is the 4 vector of the space-time translation. So now, yeah.
That H, shouldn't it be a translation along the null direction and not the U?
Well, so here there is no null, like a null direction in the space-time, you are saying?
Yeah, I mean, what is H? When you say H is the Hamilton?
Oh, H is just P0.
Translation
P0.
along the U direction?
So this H is just actually P0. I mean, that's the Hamiltonian I'm taking.
Yeah, but shouldn't, I mean, you're generating translations along.
Yeah, actually, yeah. So actually, that is a question. So why it is that this P0, which actually generates translation in time, like the T, I mean, that actually also gives you the U translation. I mean, that's is that the question?
I mean, the natural generator would have been the one
actually, what happens is that you can see that if you write down this boundary coordinate, so you have this some minus du square, and then you have things some du, dr, and all this thing. Okay, so this u coordinate, so u actually, so if you now set, actually, if you look at this central world line, so this is just an observer at rest. And this u is essentially the proper time of that observer. So that is one way to see that. That's why H actually generates this translation. Actually, in fact, I mean, there is a very good way to see this actually. I mean, you don't have to go through all these calculations. I mean, just geometrically, you can show that, I mean, if you define these states, then they have to actually, but I actually, well, I mean, I can, but I mean, that is in my EA actually, but I did not discuss it here. So, the thing is that, I mean, this H is P0, and if you just do it blindly, I mean, that's what you get. And it has an explanation, but, well, I didn't.
Translations.
Yeah.
Shifts you.
Yeah, exactly, yeah. Because the point is that if you just look at this thing actually, so if you set all L1, L2, L3 to 0, then you just get F, Z, Z bar, L is just L0, and you just shift by L0. And the reason is actually this. So if you look at the time of this central observer, then that T is essentially U. Because like, I mean, these are these cones. Okay. So this time, I mean, you can just think of this as this time. Okay. And these are these different U equals U2, U equals U1. That is actually essentially the thing. And the point is that, I mean, there is actually a geometric argument, and you don't need to go through this to see that actually, I mean, that this states are here. So that is actually in my paper, but I did not go through that here because, I mean, that will take too much time. So, I mean, if you believe me, like if you do this, then, I mean, H is P0, then you actually get this, and that is roughly the reason. So you get this U, and now if you go back to these transformations, to these older slides actually, then what you get is that, yeah, so under SL2C, you saw that this U, Z, Z bar, which are the boundary coordinates which we got from the bulk, so they have this particular form. This U transforms in this way, and Z, Z bar actually transforms in this way. And under translation, it also transforms in the same way. So at least what we have obtained is a set of states, okay, which actually transform under the Poincare transformation in this particular way. And so you can think of this U, Z, Z bar. So the states, so you have these states, so these Heisenberg picture states, this H bar, U, Z, Z bar, they can be thought of as living in a three-dimensional space-time with coordinates U, Z, Z bar, on which the Poincare group actually acts like this. Now the coordinate U actually now plays the role of time, and which is actually conjugate to H. So now this is precisely the way the Poincare group actually acts at null-infinity in Minkowski space in boundary coordinates. Therefore, from this point of view, one can actually think of this particle at, particle which is actually described by this state as living on the null-infinity, but strictly speaking, well, I mean, that interpretation is not required. So once I have these things, and I can just, I mean, this is an autonomous system. You don't really need to have a space-time interpretation, Minkowski space-time interpretation for this. Okay, so now let's actually compute some interesting things with this. So you can actually ask, like, suppose I describe my states in this way, this H bar, Z bar type of states, and then the thing is that I can compute this transition amplitude, which is just like the analog of xt, x prime, t prime. So this calculation you can do, and what you get basically is this expression. First of all, you can see that due to the momentum conservation, this amplitude is actually ultra-local in the z direction. So this particle can actually only move in time, and that is actually one of the most important things that I will come to later. And the second thing is that this amplitude is Poincare invariant. For example, let's do a space-time translation where this u z bar actually goes to u plus f z bar and z bar. Now you can look at how this u prime minus u will change, but the point is that because you have a delta function of z prime minus z, so this u prime minus u does not change under the space-time translation, which is actually the expected behavior. And then one can similarly check that the SL2C transformation also works nicely. And the point is that these representations are all unitary, as can be easily checked. Now, I'll actually like to mention one point. The fact is that because of this, the thing which we actually showed here, so this FZZ bar, which gives you the space-time translation, so that has this particular form, that has this fixed form, that once you have this L mu, the Z dependence is fixed, okay? But the point is that you can just see from here that all the space-time translation gives you this particular form of the FZZ bar. But the thing is that because of this presence of delta function, you can actually make a more general translation in U, where actually U shifts by some function f z bar, which is now any smooth function on the sphere, which is actually parameterized in terms of z bar. Now, it tells you that why f can't be a function of u, because if f is a function of u, then this is not an invariant quantity. So just one has to realize that this is actually a simple-less particle. So this is supposed to be invariant under this translation, but if I make f u dependent, then this translation amplitude is not invariant, but under any translations of this form where this f z z bar is an arbitrary smooth function on the sphere. So this you can call super translation, but note that this is not an asymptotic. Well, I mean, this should not be interpreted as an asymptotic symmetry in the sense that, well, this is just, well, I mean, we have not talked about the, well, so this is just a geometrical symmetry of, one can just think of this as a geometrical symmetry of this z bar space, actually. Just like in the case of the Virasoro algebra, we can just think of W going to any function of Z as some geometrical symmetry that is a conformal symmetry of the sphere. So similarly, this space also has some its own A, which is like that this FZZ bar can be any smooth function.
Yes. I don't see why you are saying this is not an asymptotic symmetry, because you are already in the asymptotic region, and it's a symmetry in this.
Yeah. So
I think you.
Yeah. So actually, it's not an asymptotic symmetry in the sense that there is no gauge symmetry here for which these are like large gauge transformations. So that picture, like, yeah, so at the end of the day, of course, it is an asymptotic symmetry, but so far, I mean, these are just free particles which are described in this space, this UZZ bar. Because like so, yeah, it is invariant actually, yeah. No. So it is an asymptotic, well, so
I think that's the property of asymptotic symmetry. In the asymptotic region is an honest symmetry.
Yeah.
It's not extended through the whole space-time.
Yeah, right. So the thing is that, yeah, so in this case, I think what I really meant is that, I mean, there is no diffeomorphism here for which one can think of this U going to U plus FZZ bar as a large diffeomorphism. So that picture, like, at least so far, that picture is not there. So in that sense,
I have another question. So in equation 33, of the overlap between these two, could there be another term that goes like delta function of u minus u prime?
Yeah, that is actually a very good question. Well, so actually, why do you think?
Well, because that's also consistent, I think, with the
that is also.
symmetry.
In fact, I mean, if I look at this Aztec type of Magnum type of, I mean, they probably will have a ultra local in time also. I mean, some kind of thing. But yeah, so. Yeah, so this actually I'll look at, but as it stands, I didn't see any delta function appearing. I mean, so these integrals are actually quite, like, as you can see, for example, this lambda prime minus lambda, I mean, so that has a small negative imaginary. So these integrals are a bit tricky, probably, with proper regularization. Yeah, that is true, that this is also consistent, the delta u minus u prime. Yeah, and that the question that you asked, yeah. So in that sense, actually, it's not an asymptotic symmetry. So we have not introduced any diffeomorphism. So this is just an accidental symmetry. So we are not thinking of this as large gauge transformations because so far there is no gauge notion of gauge transformation. I mean, in that sense. But of course, at the end of the day, in the interacting theory, it becomes an asymptotic symmetry. Yeah. So these are all free theory. I mean, these are all free particles actually. Yeah, so now actually, how much time I have? 8. Oh, excellent. Yeah, so actually now it is quite straightforward. So what you can do is that you can construct these creation fields and annihilation fields which actually live on this three-dimensional space U, Z, Z bar. And they have this indices, this lambda, sigma, and then you have this u lambda. And the point is that the way this SL2C transformation will act on this just like this, and the space-time translation will act just like this. Now the point is that you can immediately write down that what this thing is. So this thing will just be given by this. So A dagger P sigma is a standard, I mean that is a Fock space creation annihilation operator which you have actually here. Okay, and then, yeah, so this relation actually looks very much like this relation which actually defines the creation field for a scalar, for a say massless scalar field in the Minkowski space. So we'd now like to interpret this as a creation field for a particle with quantum numbers lambda sigma on this UZZ bar space-time. And the point is that they actually transform in this way. So for any helicity sigma, they will transform inhomogeneously. They will transform homogeneously under the SL2C group for any value of sigma which you have. And then, of course, you can compute this thing. This is essentially this object which you have here, and that actually gives you this. Okay. And so actually you can do some things with this. For example, that suppose, well, I mean, now actually things are quite, in the sense that, so probably, I mean, you could think of some kind of a quantum field theory which lives on this space. And the thing is that the basic objects of such a field theory are local operators, but locality I haven't defined, and it's not, but whatever, I mean, in the sense that it is just depend on U, Z, Z bar, it's a function. And the point is that which are tensors of the inhomogeneous SL2C, so they will have this transformation law. And the point is that the field theory does not have the ISO 1, 2, so although it's a three-dimensional field, field theory, say let's call that field theory. Because this looks like very much like a field theory. So this does not have the ISO 1, 2 invariance, but the Hilbert space of this field theory is a unitary representation of the inhomogeneous SO 3, 1. And then what you can do is that one can consider, you can actually construct correlation functions of this form, you can actually explicitly do, I mean, I'll not go into that. So it has been constructed, I mean, starting from the AS matrix, you can explicitly construct this thing where this I is lambda I sigma I, and you have actually inserted these operators at these points ui, zi is zi bar, and this omega is the Poincare invariant vacuum. For example, and the point is that the Poincare invariance, now it is just like the global conformal invariance, and you also have the translations, which are actually extremely important in this case. So for example, one can, I mean, it has been checked, if you study the 4-point function, then this particular translational constraint which you have on the fields, so that implies that the 4-point function is actually 0 unless these 4 points, these 4 complex points, Z1, Z2, Z3, Z4, unless their cross ratio is not real. So that is the constraint that Z equals Z bar, where Z is the cross ratio of these 4 points. So that actually follows easily from this thing actually. So it is behaving very much like a 2-dimensional conformal field theory, but there are of course some constraints on top of that, because which comes from the fact that you also have the space-time translations.
I have a question. So
Yeah.
Originally we had 3 momentum variables, right?
Yeah.
And so you viewed these 3 momentum variables as one point on a sphere,
right.
and then the overall modulus of the momentum.
Yeah, so
And
you are
then-
saying, I mean, now you have one more.
Yeah, so I'm complaining. Yeah, I
yeah.
think it's
So,
funny that you have one more variable, which is, so in some sense you define H as being somehow
Yeah,
related
so
to this
actually
Fourier
what is
transform.
happening here is that these lambdas are not conserved quantum numbers. So so for example, if you just look at this state, or like say, let's look at this state. So I mean, well, so this is of course an operator. That, so there is some kind of a very non-local relation between the change in lambda and the change in u, and the relation is something like it is like del u is something like exponential some I del lambda. So you can so just by acting on this, by changing u and lambda, you can see that actually annihilates this thing. But the thing is that you could actually just think in terms of change in lambda, like the space-time translation, that is changing, that is actually acting in the lambda direction only. But the point is that it is just easier to look at the u direction, and the states, they automatically, like this, the way these states are constructed, they will automatically take care of that. So that is that seems to be the thing what is happening here. So I did not answer your question, Praveen.
Well, maybe I'm interpreting your answer as saying that you have a kind of Wigner representation where you have both x and p, 2 variables which are not.
Yeah, but
this case
there
would
is
be
a
u and
relation
lambda.
between the two also. Because the thing is that lambda is not a conserved quantum number, so it's something like an eigenvalue of the boost operator.
Well,
So changing lambda, I mean, there is some relation between changing lambda and u. Yeah, so that's the thing is that.
well, let's
Yeah,
do something simpler first. So
yeah, so let's just look at this thing actually. So just from here, you can see that it is not a delta function of lambda prime minus lambda. So these fields, they are actually all mixing as you evolve in time. So it's not that these fields are independent fields. Because I mean, they have to mix other, because we know that this whole P sigma representation, so that's an irreducible representation of the ISO 3,1, whereas this fixed lambda representation, that is an SL2C representation, but then the space-time translation act by changing the lambda. And here actually, just by looking at this, you can see that this lambda is not a, so this lambda, as it's changing u, this lambdas are actually mixing. So this I could actually just call this the matrix element between these two different SL2C representations. But then I am actually interpreting that as a time because the point is that, well, it is just easier to think of them as time, and then then these gamma functions and all these things that takes care of. Yeah, so probably, yeah. I mean, it's not. So I think, yeah, but one thing is actually at least clear from here that these fields are not independent field as I'm evolving in time, so they are mixing. And the point is that I could just think in terms of lambda, but it is just physically more transparent to keep the U. And the point is that the action of the full Poincare group is very simple in terms of U. I mean, that is one way to think of it. But then the action on lambdas, I know how it acts on, in a sense, acting on lambda. Yeah, I mean, that is, and also you can see just from here, these fields, I mean, there is no delta function of lambda prime minus lambda. So they are actually not independent in that sense. So they are all mixing. I mean, they have to mix because it is an irreducible representation.
Let's see. Before, didn't you have a relationship that had a delta function of lambda minus lambda
Yeah,
prime?
so
when
it is actually two different SL2C representations you had actually. Yeah. So that representation. So that thing.
yeah, that one.
Yeah. So that thing is actually at a fixed time, at a fixed U. But now actually I have changed this actually. So now I am looking at different U's. And then actually you can just check that if you set U equals U prime, this thing actually reduces to delta lambda prime minus lambda. So that is what is happening. So that can be, I mean, that is just from the integral representation that actually one can just check that happens. So that representation was at fixed U. Now I am looking at the states at different U's and doing this thing.
I'm not sure it was at fixed U because when you were doing the energy basis, right? Let's look at in the definition. So the first time where lambda appeared.
Yeah. So just let us go back to this thing.
Yeah, that one. Yeah. So here on the right hand side you have this energy basis, right?
Yeah. Right.
And that those are really Fourier transforms of the insertion of the field operator, but at different U's, right? So in the right hand side.
Yeah.
That means, I mean, if you think of field insertion at null-infinity, you are integrating over null-infinity with some Fourier coefficient. I mean, you're doing the Fourier transform with an e to the I e u.
Yeah.
Right?
Yeah. Right.
So they are not at a specific U. They are all U's.
So far, I mean, there is no U. At least so far, like, at this point, there is no. I am not thinking well. I mean, this is just a P space. Basis states. I'm just writing them in terms, and this relation actually now. So it fixed U in the sense that if I just look at this transition amplitude, then if I set U equals U prime, then actually I am going back to this relation. That's what I mean by at a fixed U actually. So at like U, so this thing was a e to the power minus IH U minus E prime. So setting U equals U prime, I'm getting back this thing.
I'm not directly contradicting what you are saying. It's just the physical interpretation, but because you stated that this is a fixed U relation. I think here we are integrating over all U's in null space, and then in the other thing you did was to take that and then do an extra U translation. So that is perfectly fine, but physically interpreting that as being living at a specific U, I think it's...
I did not actually have in mind the thing that at fixed time, in the sense that not that bulk. Yeah, so what I just meant was this fact that here, if I set U equals U prime, then I am going back to that actually at constant U surface and then thinking of in terms of that. Yeah, but in the bulky actually, I mean, there are not all things are clear actually here. I mean, but the thing is that once you do the algebra, some of the things actually work out. But all physical interpretations, they are not very transparent. But the thing is that, well, so how much time I have? I'm done. So 3 minutes? Huh? Okay, so yeah, so probably this is the thing which I wanted to show is that I'm actually, so this is not about these things actually, but you can just construct these charges. I mean, if you have these free particles, you can construct, sorry. So let's, so some applications of this actually. So what we saw in the last slide was that there was some kind of a symmetry that if you have this this single massless particle, then this transition amplitude is invariant under u going to u plus f z bar. Okay, and then because of this delta function, you could take f to be any function on the sphere. So this suggests that, okay, suppose I look at charge, so I look at the p space, the standard for Fock space here, and then I define this charge. Okay, the E times EA will be the standard H, the Hamiltonian of the free particle, and then I can define this TF just by convoluting this with any smooth function on the sphere, and this is a Hermitian operator. So it is a real smooth function on the sphere. Now, what you can show is that all these TFs, they commute with the Hamiltonian of the theory. And the thing is that TF F prime, they commute. And this is the most important property which tells you that TF acting on this gives you this and TF. And this is essentially, if you remember, this is essentially how the hard part of the, like in this soft theorem, in this relation between soft theorem and the asymptotic symmetries, this is essentially how the hard part of the charge actually acts on the hard particles actually. Yeah. Okay, so it has been just construction of that, but now actually, but whatever. So you can actually now look at this UF as e to the power minus IHF, and then you can act with this, oh, sorry, this is not HF, this is TF. So now you can act on this creation annihilation fields with this e to the power ITF, and what you get is basically this. And so for infinitesimal transformation, this is the object which you get. This is like the equation of motion when you replace the translation with the super translation. Oh, no. So that is actually automatically taken care of by this relation. Like, so that is already part of this thing. So for infinitesimal transformation, that's what you get. Now, actually, I just wanted to point out one thing, which is that, so now we can compute how this TF actually transforms under an SL2C transformation. So this U lambda acting on TF actually gives you a TF prime, where F prime has this particular form. And now if you define this basis of generators, this is actually particularly useful to work with. And then you can define this TPQ as where I choose my F to be of this form, ZP and Z bar to the power Q, 1 plus ZZ bar, where P and Q are integers. Now, after something, I mean, if you do just do some simple computation with this, so that's the computation between this ln and TPQ, which you get actually. So this is the standard, I mean, this is the SL2C algebra, and this is the algebra between the SL2C and the super translations, which actually also include the translation. And this is essentially the algebra of the BMS group, which was found by these authors. And so this actually shows that the Fock space of the free massless particles is in 4 dimensions. I mean, I'm just mentioned this free is actually what we have done. The Fock space of the free massless particle in 4 dimensions. It carries a unitary representation of the BMS algebra. So actually, so that is basically the thing I wanted to point out. I mean that the unitary representation of the BMS algebra is the one probably which is, I mean, well, if BMS has anything to do with particles, then probably it's just a unitary representation because the standard Fock space that carries this representation. Okay, actually now you can, well, let me skip this part. And now you can actually do play the same game for a charged particle, which is actually, so there is a global E1, you can actually play the same game. And then what you get is that basically you can define these things. So now you have actually one copy of global E1 at every point of the sphere. And then you have the Lorentz transformation of the charges, which are given by this U lambda inverse QF U lambda, and the transformation parameter, this F actually under Lorentz transformation that transforms like this. And then you can define this Q, PQ in the same way that we define the super translation generators. And then you get this algebra. So this is like a E1 Kac-Moody. And so you can actually now, I mean, you can do a more, probably more conventional thing is that just look at those modes for which say P, either P is 0 or Q equal to 0. And then what you get is a E1 Kac-Moody with a level 0. So that is essentially the symmetry of a charge, I mean, free charge scalar particle. And this is what appears in this relation between soft theorem and asymptotic symmetries. And just so I don't have time, but just I want to mention one thing that actually in this representation, the relation between the soft graviton theorem and the BMS super translation, I mean, that actually comes out in a particularly nice way. So yeah, so that is essentially that was essentially the thing. Yeah, I think I'll stop here. Yeah.
Comments? Okay, if there are no further questions, let's thank Shamik again.